We are on Unit 5. This is our second section of this unit, and in this section, we are going to be looking at what are called Riemann sums and definite integrals. So in this section, we are focusing on finding the area underneath a curve. So let me just sketch out a little curve here. Let's call this curve y is equal to, this is the graph of y is equal to f of x, so some function of x. And let's give it some boundaries so that we can find, we can consider this area. So let's say that this is x is equal to a and this is x is equal to b. So we are focusing on trying to find out what is this area that's under this curve. So this is the area that we're talking about here. Okay. If f of x was linear, then this would not be a problem. We have ways to find the area of a triangle or a rectangle, right? But this f of x that I drew is not linear, it's a curve. So finding this area is a bit of a problem, okay? So before we find the area, I'd like to look at just approximating the area. So we're asking ourselves, okay, approximately what is the area? So if I do that, let me sketch this out again. From A to B. The first way that we're going to approximate this area under this curve is with some rectangles. And these rectangles are going to be kind of tall and skinny rectangles. But they will be rectangles. If I just drew, like let's say what if I split this up into like 5 rectangles? Maybe I'll split it up into 6 rectangles. So I'll do this, and then each of these will be a third. So if I did that, I split it up into 6 sub-intervals, okay? But right now, each of these is not a rectangle because the top is not flat, right? So we want to make the top flat. So the question is, where do we put that flat spot? We could make the top of the rectangle the same height as the left-hand side of each rectangle. So if we did that, then this first rectangle's height would be right here. So this would be the rectangle. This would be the rectangle here. And we could find the area of that rectangle, right? Because we know how to find the area of a rectangle. So if we continue that pattern, the next rectangle, this would be the height of that rectangle. So that would be what the rectangle would look like. Okay. For this next rectangle, the left-hand side is always the height where the curve meets. So that would be the rectangle. Here, this would be the height, like that. So that would be the rectangle. And this next one, this would be the height. And in the 6th rectangle, that left-hand side would be the height. So the more rectangles we use, the more sub-intervals we use, the closer our approximation of the area would be to this area, right? So in this first way that we did the rectangle, that we formed the rectangles using each left-hand side of the rectangle, right? So this is called a left Riemann sum. So when the left side is used as the height, we have what is called a left Riemann sum. Riemann. Okay, let me spell this right. R-I-E-M-A-N-N, sum. So this is a left Riemann sum. Riemann was named, this is a man's name. This was Bernhard Riemann. He's a German mathematician. He lived back in the 1800s. And, oops, goodness, 1826 to 1866. So he only lived for 40 years. He made some great contributions to math. And this is not the last time we will talk about Riemann and what he's done in calculus. All right? He gave us our first real rigorous formulation of a definite integral. Okay, so the next type of Riemann sum would be, trying to get a similar look to my curve and my area. So the next one, let's say that we still have those six sub intervals. Okay, but this time, instead of using, so for this first rectangle, instead of using the left-hand side as the height, I'm going to use the right-hand side as the height. So that's going to be my first height of that first rectangle. So there's my rectangle. For the second rectangle, the right-hand height will be my height of my rectangle. Here we are at the third rectangle. There's the right-hand height, so that's the height of my rectangle. For this one, right-hand height, and right-hand height. So again, we can find those areas, and when we do, that will be our what's called a right Riemann sum. So the right side is used for the height of the rectangle. We have a right Riemann sum. Okay. All right. So we could use the left-hand side. We could use the right-hand side. There's also another way that we could form these rectangles. Let me split this up into 6 pieces again. Okay. So another way that we could form these rectangles is not to use the left or the right, but to use the middle value. So whatever this delta x is here, I'm looking at exactly the middle of that delta x. So if this was a, if this was a 4 and this was a 6, then I would be looking at the middle when x is 5. Right, the middle x value, the function height at that middle x value. Okay, so this would be the height of that first rectangle. So we would have the rectangle looking like that, and this would be the height of our next rectangle. This is the height of this rectangle. Here, this is the height. Here, this is the height. And here, this is the height. So as you can imagine, this looks like it might be a better approximation than the left or the right-hand Riemann sum. So this is called when the midpoint is used, it's called a midpoint sum, a midpoint sum. Some textbooks call it a midpoint Riemann sum, and some just call it a midpoint sum. Ours happens just to call it a midpoint sum. So if you call it a midpoint Riemann sum, that's okay. But I'm just going to call it a midpoint sum. Okay? So 3 ways that we can use rectangles to approximate the area under a curve. Now there's another way that we're going to look at that we could use to approximate that area, and it's not with rectangles. So there's our little curve again. Here's my x is equal to a and x is equal to b. let me go ahead and do our 6 subintervals. We still are looking for something that we know how to find the area of, okay? So in this one, we're not going to have a flat top. We're not going to have a flat top. What we're going to do is we're going to connect. We're going to connect those 2 heights. And when you connect that, we get a trapezoid. This is a trapezoid. And a trapezoid is another figure that we know the formula for the area of. So we can easily find the area of each trapezoid. Let's see if I can draw this. I have a very thick pen, and you're not going to see that there is area between the trapezoid and the curve, but there should be a little area under there, right? My pen is just awfully thick. In fact, when the curve is concave down, our trapezoid should be underneath the curve, right? When our curve is concave up, our trapezoids should be a little bit over the curve. Do you agree? Anyway, we can find the area of each trapezoid, and this is called a trapezoidal sum. When you add up all the areas of those trapezoids, called a trapezoidal sum. Okay? So, 4 types of approximations for the area under a curve. I want you to always remember that these things, these approximations, are all for the area under the curve. That's what they do. That's what they find. Okay? They approximate. They approximate it. Okay? All right. Oh. Formula for the area of a rectangle? Area of a rectangle? Base times height. So in each of these, we'd be looking for delta x times the height, right? Times the function height. We'll be doing some examples, but the base length of each rectangle will be our delta x's, and they don't have to all be identical. Okay, sometimes they are and sometimes they're not. Okay, the height will be the delta x itself. Now, for the trapezoid, we don't use base times height. That's not the area of a trapezoid, right? For the area of a trapezoid, that is, if you recall way back from geometry, I know you've slept since then, but way back from geometry, the area of a trapezoid is 1/2 the height times the sum of the bases. 1/2 the height times the sum of the bases. Where, if you recall from geometry a long time ago, the height is always perpendicular to both bases. Okay? So for us, which part of this trapezoid is perpendicular to both bases? Well, it's down here. It's this delta x. So for us, the height of the trapezoid will always be our delta x. The bases are always the parallel sides. The bases of a trapezoid are always the parallel sides. So you're talking about the 2 function heights. So this would be like the right-hand height plus the left-hand height plus the right-hand height, whatever that is, whatever numbers are in here for right here and here. Okay, so it's the first function height plus the second function height. So this is going to be our go-to when we're finding a trapezoidal sum. Okay. All right, so before we do some examples of that, before we do examples of that, let's think about this. How could we get it? Let's come back here to this right Riemann sum. Let's come back here to this right Riemann sum. How could we make this right Riemann sum a better approximation for this area under the curve? How could we do that? And of course, the answer is we use more rectangles. If we use more rectangles, then our approximation will be better and better and better. Right? We use a ton of rectangles. Right? If we use a ton of rectangles, we'll be closer to the area under the curve than if we use 6 rectangles. Right? Okay. I'm going to draw this again a little bit nicer. Get my A and B going here. All right. Let's say, you guys, we're doing a right Riemann sum. And let's say that we have n rectangles. Okay, we have n rectangles. If we have n rectangles, I'm going to draw a little representative rectangle. I think I'm going to get a thinner pen here. I'm going to draw a representative rectangle, and remember that it's a right Riemann sum, so the height of it will be the right-hand side. So when I draw my rectangle, I'm going to draw it like that. That's the top of my rectangle for a right Riemann sum, because the right-hand side is the height of the rectangle. Okay? That's just a representative, and I could draw them all in here, right? I could. I'm just going to focus on this one right now. So this is, I'm going to call this delta x, all right? I'm going to call that delta x. And for our purposes, I'd like for delta x to be the same each time. So each rectangle will have base length delta x, all right? So delta x here, I want to write an expression for delta x involving a and b and n. So what would the expression for delta x be? Well, the distance is b minus a, right? B minus a will be the distance, and since there are n rectangles, each delta x will be b minus a divided by n. So delta x is b minus a divided by n. Okay? So again, b minus a was the distance from a to b, and n is our number of rectangles. Okay? I don't know if you guys can hear it, but we have a little thunderstorm going on right now. Anyway, okay. All right. So the base of each rectangle will be b minus a over n, which is our delta x. That's our delta x. Okay? All right, so that's the base of each rectangle. What is the height of each rectangle? Because I'd like to add up all the areas. Okay, so I need the base and I need the height. So what is the base of each rectangle? So I'm looking for what is the height of each rectangle? So I'm looking for an expression for this height right here. Again, we're going to call this curve f of x. Okay, so do you agree that this will be f at some value, right? Some value. Let's find out what value, how we can write an intelligent expression for that. Okay, I'd like to go to our I'm going to draw another rectangle. I'm going to draw the very first one right here. So the very first rectangle, since we're doing a right Riemann sum, the very first rectangle will have like that height. Do you agree? That will be the first height. So there's my little delta x there. And there's the rectangle. So I'm looking for an expression for that height right there. Okay? Well, that is f at what? That's delta x, right? So that is f at a plus delta x. Do you agree? I hope so. So what would the next rectangle be? The next rectangle's height, I'm looking for an expression for that one. This would be f at a plus 2 delta x, right? Because twice delta x. The next one would be f of a plus 3 delta x, etc. So this one over here that we were looking for, that will be a plus some number, whatever rectangle we're on, right? I'm going to call that I, all right? I will be the number of rectangle that we're on, and it's going to be delta x times I. That will be the height of each rectangle. F at a plus delta x, which I can put this b minus a over n in for, right? Times I. That's the delta x right there. So the area, so this I, by the way, I is just a counter. And what does I start at? Well, I will need to start at 1, right? And how many I's will there be? I represents the number of rectangles, so I goes from 1 to n, okay? All right, doing good. So now the area of one rectangle. The area of one rectangle would be the base times the height, right? So the area of one rectangle is, I'm going to write the height first. I'm going to write the height. So f of a plus, I'm copying this down, b minus a over n times I. That's the height of my rectangle, times b minus a over n. That's my delta x, right? Remember that this is delta x each time. That's the area of one rectangle. That's the area of this rectangle, yeah? For any I. If we want the entire area, though, we need to add up all of our rectangles, correct? So we're going to add up all of our rectangles. How do we add up these rectangles? In math, how do we show adding things up? Well, we have a capital sigma that stands for a summation, right? So we have this. Ooh, I hope we don't lose power. That would not be good for my video. Okay. So we're going to add them all up. We're going to add up all the rectangles. So here's our counter. I is going from 1 to n. That's how many rectangles that we have. Okay? And this will give us our Riemann sum. This is our Riemann sum, our right Riemann sum. If we were doing a left Riemann sum, we'd probably have I starting at 0 because we would want our first height to be just f of a, right? So we would need to start I at 0. So we would go to n minus 1 because that would include the n rectangles there. Okay, so this is our Riemann sum. Now, to get this more and more and more and more and more accurate, we want a lot of rectangles, right? A lot of rectangles. How many do we want? Well, if we're going to get the area under this curve, we need to let the number of rectangles go to infinity. Sounds like a limit to me. If we let the limit as n goes, if we take the limit as n goes to infinity of the sum of that sum, we are no longer approximating that area. We have the area under that curve. Okay? All right. Now, this limit of this sum, the limit as n goes to infinity of this sum, that, we get this notation from Gottfried Leibniz. This is our integral. The limit as n goes to infinity of a sum. I told you when we first took a look at this symbol that this means sum. It means the sum of an infinite number of things. The sum of an infinite number of things. Okay? The infinite number of subdivisions. Okay? Because as n goes to infinity, this little piece right here is going to be getting closer and closer to 0, right? So it's the sum of an infinite number of teeny tiny little bitty itty bitty slivers. An infinite number of them. And you can imagine, if I just used the thickness of my pen, to draw my rectangles, do you agree that I would be getting the exact area under that curve, right? It makes sense. This is our definite integral because this integral starts at A. It has boundaries. It starts at A, it ends at B. Just like my rectangles started at A and ended at B. So this is the integral from A to B of the curve. Our curve is f of x. Okay? And this is the height. When you see this, I want you to think, this is the height of the rectangle. Don't forget to multiply by the base of the rectangle, even though it's tiny. This was delta x right here, right? That's delta x. In an integral, delta x becomes the differential of x. And the differential of x is the base of each rectangle. It's extraordinarily thin. It's infinitesimally small. Okay? This right here is magical. We took a finite number of things, made it infinite, and it becomes our area under the curve. Okay? So you need to know this guy. Okay? You need to know this guy. I took the time to show you where it came from in hopes that it makes a little sense to you. In hopes that when you see this, you're not going to just be memorizing a bunch of symbols. When you see this, I want you to think, oh, there's my height. And of course we're starting at A. And we're adding delta x times whatever rectangle we're on. That's my height. For my base, that's just my delta x. So b minus a divided by n. Okay? All right. I'd like to do some examples with you. And I'm wondering, in my exam, you guys should have a little page with examples on it. So let's turn to that. Let's turn to that. Okay. Let me pull it out here. Here's my examples page. I'm always tempted to go and do the last few examples here, but I think I'm going to wait. I think we're going to do it in this order. In this one, these are our examples. So in number 1 here, it says let f be a continuous function. Selected values of f are given in the table below. Okay, that works. The one thing I notice is that the x values, they're not distributed evenly. Like this goes from 0 to 20 and then 20 to 50. So this first delta x is 20, the second delta x is 30. So they're not all the same. Okay? All right. Part A, estimate this using a left Riemann sum and 5 subintervals. Left Riemann sum and 5 subintervals. Well, remember, every time you see a definite integral, this is, I don't know that I mentioned this just now, when an integral has boundaries, we call it a definite integral. When an integral has no boundaries, we call that one an indefinite integral. Okay? This is a definite integral, and definite integrals always find the area under the curve. So when you see this definite integral, think area. So when we are estimating area, they're going to tell us what to use to estimate it, because there are a variety of things that we could use. They might ask us to use a left Riemann sum to estimate the area, a right Riemann sum, a trapezoidal sum. So they will tell you what to use. They will have to tell us how many subintervals to use. Okay? But just always know what we're doing. When they say use a left Riemann sum, make sure it is only approximating the area. Okay? That'll make more sense later on. All right. So, let's get busy. We are estimating, so I'm not going to use an equal to sign. I'm going to use this little approximately equal to sign. Okay? And say what you're estimating, you guys. Don't just come in and jump in and do a left Riemann sum. I say that not because I want you to show all your work, which I do, but more because later on we're going to be using a left Riemann sum for only part of an approximation. The only thing that this will approximate is this integral. And we're going to be using the integral for other things, so you might be approximating a bigger thing. And if you only see left Riemann sum and you only go and find the left Riemann sum approximation, you're not going to be answering their question. Okay? So always say what you're approximating. All right. Left Riemann sum. So here's my thought. Here's my first rectangle. The rectangle has base length 20, right? This is my first delta x. I'm going to call it delta x sub 1. And that base length is 20, right? So that base length is 20. We want the height now. Which of these will the height be? Which of these will be the height? Well, if we're in a left Riemann sum, the left height needs to be the height of the rectangle, right? The left height. So this is height 1. There's our first rectangle area, base times height. Now let's add the next rectangle's area. Well, the next rectangle has delta x what? This is delta x sub 2. What is delta x? Delta x is 30 for that rectangle. Okay, which height should we use? Well, we need to use the left-hand height, so we're going to use the 90. Next base length is 20. The height, 80. The left-hand height. Next base length, 30. Height, 80. Last base length will be 40, and the height will be 90. Okay? In a left Riemann sum, you do not use the rightmost height of your function. Okay? This would be our safe stop spot. So if you have an FRQ, you would absolutely stop there. Do not try to multiply and add those together, you guys, okay? If it's an FRQ, which many times these are on an FRQ, okay? Don't do it, just stop, okay? If I did put that in my calculator, and I did only so that we could compare these three types, okay? If I did, when I put that in my calculator, I got 12,300. Now, one more thing before I go on. When you're writing a left Riemann sum, AP needs to see, therefore I need to see, what they call the form of a left Riemann sum. Part of your answer points, usually this is worth 1 point out of the 9 in the entire FRQ. Usually that is worth 1 point, and then another point they give for the approximation. form of a Left Riemann sum is base times height plus base times height plus base times height. They need to see that, okay? So when you're writing this first number, do not say, oh, this is 20 times 100, so that's 2,000, and so you just write 2,000 there. If you write 2,000 here, you lose this point for the form of the Left Riemann sum. You might get the answer for you might get the point for the approximation, but you lose the point for the form, okay? So write these numbers out, all right? They need that. They need to see that. Therefore, I need to see that. All right. Let's estimate this now using a right Riemann sum. Right Riemann sum. Still 5 subintervals. That means we're going to have 5 rectangles. 1, 2, 3, 4, 5. 5 subintervals. Okay? The first base length is still, the base lengths are still the same, right? So the first base length will be 20. Which height should we use? Well, this time we're using the right-hand height. So 20 times 90 plus 30 times, there's our rectangle, so we use the right-hand height, the 80, plus 20 times 80 plus 30 times 90 plus 40 times 130. This would get the point for the form, and it would get the point for the approximation because it's a safe spot. Okay? So only if it was multiple choice would you go and add that all together. And if you did do that, you would get 13,700. Okay? Part C. Let's estimate this. This time using a trapezoidal sum. Trapezoidal sum. Okay. Well, remember, for a trapezoid area, the formula is 1/2 the height times the sum of the bases. But for us, the height of the trapezoid is our delta x, is each delta x. And the bases are our function values. Okay? So for the first trapezoid, I have the 1/2. The height of the trapezoid is our first delta x, so that will be 20. And then we multiply that by the sum of our two heights. And that's our first trapezoid. Next trapezoid, 1/2, 30 times the sum of the bases. And just like I said before, they will need to see the form of the trapezoidal sum, so do not actually add these together and write that here. They've got to see that written out like this. They need to see base 1 plus base 2, so write it out. Next trapezoid, 1/2 20 times 80 plus 80. Fourth trapezoid, 1/2 of 30 times 80 plus 90. And our last trapezoid has height 40 and 90 plus 130. Okay? So if you take a look at what we did here, we multiplied the 20 in this first one. The 20 was the same in all three pieces, right? The Left Riemann sum used the 100, the right used the 90, and what did the trapezoid do? The trapezoid took the average of the two. 100 plus 90 divided by 2. That's the average of them. So essentially the trapezoidal sum averages the left and the right sum. Okay? And if we multiplied all that together and added it all up, we would get 13,000, which is indeed, you can quickly look at that. It is absolutely that's not a point. It's absolutely the average of the left and right Riemann sums. Okay? All right, part D. Given that f double prime of x is greater than 0 for the entire x domain, is the approximation found in part C an overestimate or an underestimate? And explain your reasoning. Okay? Well, if f double prime is greater than 0, f double prime is greater than 0, what does that mean? That means that f is concave up, right? F must be concave up. Right? We used a trapezoidal sum on a concave up curve. So are we going to get an overestimate or an underestimate of the actual area under the curve? Draw a little sketch just for yourself and draw a trapezoid in here. In concave up curves, a trapezoidal sum will always be greater than the actual area under the curve, right? Do you agree? It makes sense. If the curve was concave down, it would be the opposite. Yeah? So here's what I want you to write. I want you to write a trapezoidal sum is an overestimate, answer the question, on a concave up curve, and F is concave up. That's what I want you to write. Okay, be very, very succinct. Okay, is this the only answer I would take? No. But please avoid writing a huge essay here talking about your trapezoids and the curve and stuff. Here's what AP is going to be looking for. Trapezoidal sum, overestimate, concave up curve. And F is concave up here. So this goes with the concave up curve. All right? So 3 key things: trapezoidal sum, overestimate, concave up. Okay? Again, I've seen kids write something like this and they had full credit, but then they go on, and the more they chat, the more chance they have of saying something that's wrong. Maybe they'll use the wrong F prime or F double prime or whatever. Something can go wrong when you get chatty, right? I know this well. All right, so be sure to be succinct with this. They're really looking for 3 things: your answer, over or under, which approximation you used, and then why it's an overestimate. And be brief with that. Don't get chatty. All right. Okay, number 2. Let h be a continuous function now, and selected values of h of t are given in the table below. Estimate this integral using a midpoint sum and 3 subintervals, just 3 subintervals. Whenever they ask you for a midpoint sum, remember they're going to have to make your information be, include a midpoint value of your x's, right? So That's why they're only asking for 3 subintervals here instead of, 1, 2, 3, 4, 5, 6. Instead of 6, 3, so that you can use a midpoint. Okay? Now also, whenever they ask for a midpoint sum, your delta x's will be evenly distributed. They won't be like this one here. The delta x's will be even. Again, they need to do that for us if we're going to be using a midpoint sum. This value has to be between, equally between. It has to be the mid-x value of these two. Okay? So, midpoint sums are a little bit more restricted. We know more about what the table is going to be doing. Okay? All right. So, midpoint sum. We're still using a rectangle, right? So we need our first delta x. Our delta x first will be 50 minus 30, or 20. That's our first delta x. That's our first base length of the rectangle. Now what's the height of that rectangle? Well, the height of the rectangle is the function value at the middle x value. It is not the average of these two. That would be the trapezoidal sum. The midpoint sum is using that middle height. So 7. Kids make midpoint sums way harder than they are. Way harder than they are. So this first delta x is right here. It's equal to 20. The first height is right here. You don't touch the 5 and the 10. It doesn't matter what those are at all. You're only using that height. That's our first rectangle. Now let's go to our second rectangle. Okay. There's our delta x. Still 20. So 20 times. What height do we use for this rectangle? Well, we use this height right here. That's our second height. So 15. Our last rectangle, still 20 for our delta x, and our height will be 16. And that's it. That's it. Stop there. We have the form of a midpoint sum, and we have our approximation. There is no need to multiply and add, okay? Now, while I'm here, let me tell you what else I would accept for this to get full credit. If you could have, we could have written it like this. We could have, since delta x was the same, when delta x is the same all the time, you can go ahead and begin by taking that out of all of the terms. And then write 7 plus 15 plus 16. But I do not actually add these together. Leave them separate. I need to see the 3 heights that you used. Okay? The other way that I would accept is right here, instead of writing 20 times 7, you could have written 50 minus 30 times that 7. That's how we got that first 20. Plus 70 minus 50 times 15 plus 90 minus 70 times 16. I don't know that I have any students who would write it like this, but I have, when I've graded AP exams, I have seen people write it like that. You don't have to write it like this though. All 3 of these gets full credit for both the form and for the approximation. Up here, when we did the trapezoidal sum, we could have started out by taking out this 1/2, right, out of everything. And that would have gotten full credit for that one as well, all right? Anytime that there's something that you can take out of every part, as long as you keep writing everything else, you'll get full credit for that. I kind of still like to see this trapezoid each time. For me, this is what I tend to do, okay? All right. And by the way, anytime that you're explaining an over or an underestimate, do not say, look at my picture. Don't say that. That is not going to be enough of an explanation. The picture here was just for us, just to get an idea of what our answer should be. But do not tell AP to go look at your picture. They're not going to do it. Okay? Next example. What if we don't have a table? Approximate this integral, this definite integral. Again, this is area because it's definite. We have boundaries. And whenever you have boundaries, it's area. Okay? Approximate that area using a left Riemann sum and 4 equal subintervals. Okay? All right. Well, our x values are going from 0 to 2 in 4 subintervals. So what is delta x? What is delta x? It makes sense. It has to be a half, right? It has to be a half. If you want to do it the more formula ways, I don't advise you to do this the formula way, but if you want to do the formula way, you could use delta x is equal to our b minus a over n, right? So that would be 2 minus 0 over 4, because we're going to have 4 rectangles, and that's a half. But hopefully that's obvious to you that delta x has to be a 1/2 to get from 0 to 2 in 4 subintervals. Okay, well, if that's true, we're using a left Riemann sum, so we need to find that leftmost height. Well, the leftmost height will be f of 0, correct? So we're going to put 0 in for x. And we get 1. So the first height is 1. The next height will be f at 1/2. So we're going to put 1/2 in for x. That turns out to be 1.375. Next up we find f at 1. So we put 1 in for x. That turns out to be 2. And then we have f at 3/2. Put 3/2 in for x. That turns out to be 2.125. And if you just can't stand it, you can go ahead and find f of 2. It turns out to be a 1, but we don't need this one. This is not needed because we're doing a left Riemann sum. Okay? So our integral, our area, our integral here is approximately equal to, okay, remember rectangles, base times height. First base, 1/2. First height, 1. Next height, still 1/2. In fact, all the bases, I think I said height, all the bases will be a half. So if you wanted to, you could take that 1/2 out of all of them. I'm just going to write it like this. For the next height will be the 1.375. 1/2 times the next height is 2, and then 1/2 times the very last rectangle's height, 2.125. Okay? And if this is not a multiple choice, that's all I write. I don't box it, I just leave it. Okay? So FYI, for your just FYI, when I punch this into my calculator, because in our calculator we have an integral key. Let me get out of here. Okay. If I punch this into my calculator, I want to find the this is going to give me the actual area. Okay? Do math, down here math, and then it's down at number 9, so I'm just going to push the number 9 here, and that gives me this. So wherever it's hovering, that's where I need to fill in. So I need to go from 0. I'm going to use my up arrow to get to the upper boundary to 2. And now I'm going to come in here and put my function value, negative x cubed plus 2x squared plus 1. And then it's forcing me to do the dx, right? That's a good thing because it needs to know what variable to integrate with respect to. Okay? And we get that. Okay? So the actual, if I round to 3 decimal places, the actual area is this. When you figure this out, when you add all these up, I got 3.25. So our little 4 rectangles didn't give us too bad of an approximation. Wasn't too bad. Could have been better if I had used more rectangles, right? Okay, next example. The amount of water in a draining tank is given by a strictly decreasing function W. So first thing I see is this, why are they telling me this? That's an odd thing for them to tell me. There must be a reason, okay? Where W of t is given in the table below. It would say selected values. I should have put selected values of, okay? All right. Use a right Riemann sum with 4 subintervals to approximate this definite integral. This is the area under that curve, right? So, and a right Riemann sum does approximate the area under that curve. So we can go straight to the right Riemann sum. So let's see, first delta x, or t in this case. First delta t is 10, right? So 10 will be the first base length of our rectangle. And then we want a right Riemann sum, so we're going to use the right function value as the height of the rectangle. So 78.3. Okay, next rectangle, 5. Next height will be the right-hand height. Next base length, 5. Height, 60.8. Next base length, 15. Height 43.2. Remember, in a right Riemann sum, you're not going to use the leftmost height. Okay? Okay. Do we want to do any more with this? No, we're not going to. Even if it's with a calculator, do not actually add that up unless you have to use that value later on in the FRQ. Don't touch this, just leave it. This gives us credit for the form, and it gives us credit for the approximation. So we're good. Both of them are good. Okay, part B. Is your answer to part A an overestimate or an underestimate of the actual value? Explain your reasoning. Well, we used a right Riemann sum on a decreasing function. Let's draw ourselves a little picture, not for AP to see, but more for us to see. They don't care if you draw a picture. They just don't want you to say, look at the picture. So there's a decreasing function, right? There's a decreasing function, and we used a right Riemann sum. So a right Riemann sum uses the right side as the height, doesn't it? Do you agree? The right Riemann sum uses the right side as the height. So every rectangle will be below the curve here. Why? Because it's decreasing, and we used a right Riemann sum. Okay? So now that we know our answer, we're going to write we're going to write it for AP. A right Riemann sum on a decreasing function yields an underestimate. And W of t is decreasing. That's it. That's all they need. Don't go on and on. Don't write an essay. Don't say, look at the picture. Don't say, as you can see by my picture. I get kids saying that. Please don't. It's not enough of a reason for AP, so it's not enough of a reason for me. Okay, next up, let's take a look at number 5. Write this definite integral as the limit of a Riemann sum. Okay, so we've got a little, I've let a little time go by, a few minutes go by. Let's remind ourselves about that limit. Remember, it is a limit, as the number, n is the number of rectangles, and we're letting the number of rectangles go to infinity. And then we have this Riemann sum, so it's a sum, so put sigma because it's the sum. It's the limit of a sum. Kids say, Miss Murray, I keep forgetting, do I put the sigma first or the limit first? I'm like, well, it's the limit of a sum. It's not the sum of a limit. So put the limit first and then the sum. Okay? Now this is just our counter. I is going from 1 to n. That's our number of rectangles. Okay? And now we need our function values. Our function values. So this is our function. This is the height, right? And our x value started at a, and we added delta x times I. Delta x times I. And that was the height. Remember, that was our height of our function. And now we needed to multiply by the base of our function, height of our, it is the height of the function, it's also the height of the rectangle, okay? Then we need to multiply by the base of the rectangle, and that's our tiny little sliver of delta x. Delta x. Remember, delta x is b minus a over n, all right? So let's write this out. So limit, n goes to infinity, sum, I goes from 1 to n, number of rectangles. Okay, we're putting a plus b minus a over n times I in for x. So I'm going to have something squared plus 1. That's my function. And in place of the x, I'm putting this thing. Only the a and the b have meanings. The a is 3, b is 7, right? So right here, my a, I need to put a 3. That's what a is. What is b minus a? Well, b minus a is 4 over n times I. Right? So this is our a plus delta xi. That's our height of the rectangle, and now you multiply by the base of the rectangle. Just delta x. b minus a over n. No I back here. The only I is in place of your x there. Okay? I know that this is a little weird, but after you do a few of these, you got it. It's not going to be a problem. Okay, let's do this one. Limit, n goes to infinity, sum, I goes from 1 to n. Okay? Sine of something. Sine of what? A plus b minus a. What is b minus a here? B minus a here is a negative 6, isn't it? So instead of a plus here, I'm going to make it a minus because we have a negative 6. 6 over n I. plus x. Well, I need to put this again for that x because it goes in for every x. Okay, there's my function, and now I'm multiplied just by my delta x, negative 6 over n. You do a few of these, you'll be fine. But you gotta do a few of these to be fine. Okay. On a test, I will tell you that these are multiple choice questions. Okay. Which doesn't mean they're easy, it just means that they're multiple choice. So you'll need to be able to pick out the right one. Okay. All right. What about this one? Let's write this limit of a Riemann sum as a definite integral. So we want to write this as a definite integral. First thing do, look at your boundaries. Where do you look to find your lower boundary? To find your lower boundary, you look at that, whatever is being added to your delta x over I, or delta x times I over here. So the lower boundary here is this 2. Okay? How do you get the upper boundary? Well, whatever the upper boundary is, minus 2 has got to be 3. So this one has to be 5, because 5 minus 2 is 3. Right? Okay. The other way to get that upper boundary is just to add these two together. Okay? All right. Now what is our function? Well, remember, this is x. This is our x. So ln x plus 3 is our function. That's our function. And then this is our delta x. That's delta x. And in an integral, delta x is dx. That's it. Most kids far prefer going from the limit of the Riemann sum to the definite integral than from the definite integral to the limit of the Riemann sum. Okay, let's do number 8. What's our lower boundary? Well, our lower boundary, we need to look right here. It's the 5. What's our upper boundary? Well, 5 plus 2, it's right there, 7. Okay, there's our boundaries. What's our function? Remember, this is x, and this is x. So we have x cubed plus 3x. This is our delta x, so there's our dx. Okay, as I told you before, you can put parentheses here, or you don't have to put parentheses there. They are implied if you don't use them. Okay, either way. All right, this was a big section for us. Lots going on. We really do need to go and do some practice now. So do your practice and let me know how it goes.